So math 312 linear algebra. Did I share the course outline for the other two courses? I'll share. Dr. Jen. No problem, they'll sort it out. The exam will be the same anyway, so they think that when we are using the same course outline, so you shouldn't worry. I'll share the two course outline. So in majorly this course entails study of solving systems of linear equations and matrices. So the main goal is systems of linear equations and then matrices. So all the discussions or all the chapters we'll discuss will be revolving around either solving a system of linear equations or doing computations involving matrices. The first chapter is systems of linear equations. So we start by defining what we mean by a linear equation, and then give examples of linear equations and non-linear equations, and then state and discuss different methods of solving systems of linear equations. So a linear equation in n variables is an equation of the form The equation which takes this structure is called a linear equation in n variables. So the numbers A1, A2, A3 up to AN are called coefficients. B is called constant term. So A1, A2, A3, all the way up to AN, all these are real numbers called coefficients. Of the variables x1, x2, x3, all the way up to xn, respectively. Number B is also a real number, is called the constant term. Then A1 is called the leading coefficient. Then x1 is called the leading variable. So one key observation from this equation, if I call it equation alpha, is that all the variables involved in a linear equation are to power 1. And then another observation is that there is no product of variables in a linear equation. So those are the key things. No product of variables in any term. The only power if a variable is involved in a term is 1. So classify the following. As linear. So an equation which is not linear is so it's said to be nonlinear or nonlinear equation. So the first one is 4x plus 5y equals to 20. B is a third x plus 5y plus 10z equals to root 7. C, xy plus z equals to 30. D, x1 minus 5x2 plus 30x3 plus 5x4 equals to 0. F, e power x plus 3y plus z equals to e power 4. G, sine pi over 2 x3 plus 5x4 equals to e raised power 4. F 1 over x plus 1 over y equals to 1 over 20. RFGH I sin x plus 2y plus 3z equals to 3. So we'll go one by one. Is A linear or non-linear? A is linear, correct. Because you say variables involved, they have to power 1. There are no products of variables. So this is linear, correct. B? Why non-linear? Yeah, so which one is not a real number? No, pi is a real number. Pi is a real number. Yes? Mm. So according to you, the equation will be nonlinear because of pi. Yes, pi is a real number. To force it to be nonlinear. You are still stuck that it must be nonlinear, so you are trying to see how you can defend your answer. Hmm? Definition, actually, you have understood it from what you are trying to explain in the first case. But you argue that you want to classify B as linear because of pi, and I told you pi is a real number. You actually say that pi is not a real number, which means you understood what the definition means. Mm. Where is linear? Don't complicate the obvious. you really you understood what the definition is because you wanted to base your argument on pi, and I've told you that pi is a real number, so you should not worry. So this is still linear. Root 7 is also just another real number, okay? Yeah. C. Linear or non-linear? That you need to be sure. You need to be sure. Non-linear reason, what makes it to be non-linear? Which term? Z has no problem because it's just power 1. What you expect? But if there's a variable, then the power of that variable is 1. So the term plus Z is there has no problem. Or the term plus Z has no problem. The nonlinearity comes from this term. Remember, we say that there is no product of variables in a linear equation, but you see there's a product of X and Y. So that is the term that makes this to be nonlinear. Because two variables have been multiplied to create the term X1. Okay? And then D, that's obvious, okay? There's no problem there. And then E, because of which power? Yeah, e power x is what makes this to be nonlinear. So this is the exponential function is a non-linear function. So this is nonlinear. And remember, it is nonlinear because of this e power x, not e power 4. E power 4 is a number, it's a real number, so there's no problem. Okay. Then G. Linear or nonlinear? Linear, because you see sine pi over 2 is just a number, okay? This is just a real number. Then also e power 4 is just a real number. So there's no complication of the terms, okay? X3, X3 is a variable. So for this case, X3 and X4 are the variables. So yeah, X3 and X4 are the variables, but then sine pi over 2 is just a number. So it's the coefficient of X3 variable. And then coefficient of X4 is 5. E power 4 is just a real number. Okay. H. Linear or non-linear? Linear, and you are sure. When you write 1 over x, what do you mean? What's the power of x? When you write 1 over x, what is the power of x? X raised power negative 1. So this is the same as having x power negative 1 plus y power negative 1 equals to 20. So this 20 power negative 1. So this is nonlinear because the powers of the variables are not 1. Okay? Yeah. I linear. Why? Is a sine function linear function? Remember, this is defining sign of the variable x. here it is sine x. X is a variable. Here it was sine pi over 2, which is a number. This is not a number. This is a function, sine of x. So which type of equation will that be now? Sine is nonlinear function, so this is nonlinear. So that's how we do the classification. The powers of the variables must be 1. There are no products of powers. Okay? But there are no product of variables in any term for linear equation. Yeah. So let's now define what we call a solution to a linear equation. So a solution to a linear equation is simply a set of real numbers that satisfy the equation. So we can say a solution of a linear equation in n variables is a sequence of n real numbers S1, S2, S3 up to Sn arranged so that the equation. So we had called our equation, I named it alpha. So this equation alpha is satisfied when the values x1 equals to S1, x2 equals to S2, x3 equals to S3, all the way up to xn equals to Sn are substituted into the equation. So that's what we call a solution to a linear equation. Set of numbers, which when you substitute for the variables, they make the equation to be satisfied. And satisfying equation means that when you replace those numbers for the variables, the left-hand side of the equation will be the same as the right-hand side. So for example, in this equation, x plus 3y equals to 4, x equals to 1, and y equals to 1 is a solution. Since when there's x, I put 1, plus where there's y, I put 1, I'll get 4. And so the left-hand side and the right-hand side of the equation will be the same. Or simply, the equation is satisfied. So the set of all solutions to a linear equation forms what we call a solution set. its solution set. And when this set is found, we say that the equation has been solved. Oh, I said it. So sorry, it is. It means it is its solution. ITS, its solution. Its solution. Its solution. Then to describe the whole solution set, a parametric representation is often used. So I'll describe in an example to explain what this really means by getting parametric solution of an equation. So in form of an example, solve the equation x plus 4y equals to 8. So that's actually, I should have called that one an appetizer. Means find all the values of x and y that satisfy this equation. And it's a very easy exercise. Say when we have x plus 4y equals to 8, this means x alone is 8 minus 4y, correct? Good. So then now we assume that we know the value or the solution for y and fix it to be a given value, which we represent as a letter we call a parameter. So we say let y be t, where this t is a real number. So we are assuming that now the solution to the variable y is known to be any real number called t. So this t is what we call a parameter. You are free to pick any other letter. T is, there's nothing special with t, but to pick a different letter from those which have been used in the equation. So when you say y is t, so this implies that x will be we know the answer to y to be t. So what is the value of x? 8 minus 40. So that would be the value of x. So therefore, the solution to the given equation is x equals to 8 minus 4t, y equals to t, and then you say t is a real number. So this structure is what we call the parametric representation of the solution set to the system of linear equation given, or to the linear equation given. So there are actually infinitely many solutions depending on the value of t. Like when t is 0, what is the value of x? What is the value of x? 8. So when you put x for 8, y for 0, it will satisfy that. That's one of the solutions. When t is 1, what is the value of x? Yeah. So when you use those now two numbers, it will satisfy that equation. And there are infinitely many of them. So that's why you're saying that the value of y is just any real number. So when we fix any real number for y, we always get a corresponding value for x, and that pair will satisfy the equation. So such kind of arrangement is what we call parametric representation of solution set. So t is what we call the parameter in this case. And by this, that's not the only way. You can as well, another person that as well, remember the same solution. We had x plus 4y equals to 8. Someone else would have made the y the subject. So we can say 4y equals to 8 minus x. So which means y will be given by 2 minus a quarter x. Is that true? Yeah. And then you say, let x be given by s. So s is a parameter. So let x equals to s be a real parameter, which is the solution now to the variable x. And this means that y will be 2 minus a quarter s, okay? So which tells you that the solution is x is s, and then y will be given by 2 minus a quarter s. And then you specify that s is any real number. So that's another way of actually solving the same equation. So with a specified value of x, you'll get a corresponding y by simply playing with values of s. Okay? Yeah. So then, can you try to solve this problem too? Solve the equation 3x1 plus 2x2 minus 2x3 equals to 6. Can we solve it together, or you can do it on your own? Okay. So is the same approach that simply make one variable the subject, and then fix others to be arbitrary real numbers. Yes, x1, x2, and x3 are different, 3 different variables. Yeah. So say 3x1 plus 2x2 minus 2x3 equals to 6 is equivalent to saying 3x1 equals to 6 minus 2x2 plus 2x3. Hope that line makes sense. Yeah, which means that x1 alone will be, you divide through by 3, okay? Minus 2 over 3 x2 plus 2 over 3 x3. Remember, x1, x2, and x3 are different variables. So when you start fixing, you fix with different letters, x2 and x3, okay? So you say let x2 be s, x3 to be t, where s and t are arbitrary real numbers. So that implies that x1 will be 2 minus 2 over 3 s plus 2 over 3 t. Then so therefore the solution is you start with x1 given by 2 minus 2 over 3 s plus 2 over 3 t. x2 is s, x3 is t, and then you specify that s and t are real numbers. And that is the solution. You can as well, if you don't want to do that, you can make x2 the subject and fix x1 and x3 with different letters, still okay. Or you can make x3 a subject and fix x1 and x2 for different letters, and you still get the set of solution for the same equation. Okay? Yeah. So when they ask you, sometimes you may be given a problem, they will give you an equation, and then ask you to test whether the given system of values satisfy the equation or satisfy the equation, or is the solution set to the given equation or not. For example, if they tell you if say x2 is say t, and say x1 is say 2t, and then they ask you to show whether if I call this double star is a solution set to 2x1 minus x2 equals to 5. This is just an example. So in such cases, what you do is to use the values given for x1 and x2, or the variables given, the expressions given in terms of the parameters, replace into the equation and see that if you do the substitution and you simplify, the left-hand side and right-hand side of the equation give the same number. If they are different, then you say that they don't give the parametric solution to the given equation. So, for instance, to test this, you simply now replace where there's x1 by 2t. So we have 2 into 2t minus x2, we have t, and this will give us 4t minus t. This is 3t. Okay? But 3t is not equivalent to 5. So therefore, this is not the solution. So therefore, you say this is not solution to the equation. But assuming we had for the same set 3x1 minus 2, okay, 3x1 minus 6x2 equals to 0. Let's say x1 minus 2x2 equals to 0. You should confirm that that is a solution by simply saying that if you are to substitute directly, we'll have 2t minus 2 into t, and this will give us 2t minus 2t, which is 0. So this is the left-hand side, and this is the same as what you have in the right-hand side. So that would be the solution. So be open to such kind of problem that you may be given now the parametric solution, and then you are asked to confirm if that given set is a solution to a given linear equation. It's just a matter of substitution and comparing the left-hand side and right-hand side, okay? Yeah. So let's now define what we call system of linear equations. So definition of system of linear equations. So to define a system of linear equations, you need to understand what a linear equation is. And we have already defined, given examples, and show how to solve one system of linear equations in more than one unknown. So then now, the main objective of the chapter and in the whole course will be to see how to solve systems of linear equations in more than 2 variables. I know in high school, we usually used to solve the same thing, but only involving, you have 2 equations and 2 unknowns. Then you can use, say, substitution, elimination of graphical to solve the values of x and y. But what we discuss here is now what can be generalized to solve any system of linear equations with more than 2 variables. So a system of m linear equations in n variables is a set of m equations each of which is linear in the same n variables given as so this is what we write. A11 x1 plus A12 x2 plus A13 x3 plus A1 n xn equals to B1. So that's the first linear equation. Next is A21 x1 plus A22 x2 plus A23 x3 plus other several terms plus A2n xn equals to B2. Next is A31 x1 plus A32 x2 plus A33 x3 all the way up to A3n xn equals to B3. Then you continue in a similar manner up to A m1 x1 plus am2 x2 plus am3 x3 up to plus amn xn equals to bm. So if I may call this star, is what we call a system of m linear equations in n variables. Then we can also define what we mean by a solution to this system. A solution of a system of linear equations such as star is a sequence of numbers S1, S2, S3, up to Sn that is a solution of each of the linear equations in the system. And we have already defined previously what a solution to linear system is. So which means that when you replace x1 for s1, x2 for s2, x3 for s3, up to xn for sn, in each of all these m equations, then the equations are satisfied. So this is very key. Why I say that it's a solution of each of the linear equations in the system. If it satisfies only one equation then and fails to satisfy other equations in the system, then that set doesn't qualify to be called a solution to that given system of linear equations. The condition is that it must satisfy all the equations given. So for example, if we have 3x plus 2y equals to 3 and minus x plus y equals to 4, if you consider this system, then x equals to minus 1 and x equals and y equals to 3 is a solution because both equations are satisfied when x equals to -1 and y equals to 3. You can check that when you put here 1, you have 3, -1, you have -3, 2 times 3 is 6, -3 plus 6 is 3. And then here, -1 is 1, plus 3 is 4. So the two equations are satisfied. But x equals to 0 and y equals to 4 is not a solution. Since this set does not satisfy both equations. You can see that if you replace 0 for x in 1, you're going to have 3 times 0 is 0, plus 2 times 4 is 8. 8 is not the same as 3, okay? But for the other one, it will be 0 plus 4 is 4. So it satisfies the second equation, but not the first one. So it doesn't qualify to be called a solution to that system. For it to be a solution, then all of them must be satisfied by the same system. Yeah. Notes. Any linear, any system of linear equations precisely has any of the following. So one, a unique, or we say one solution. Two, infinitely many solutions. And then number three, no solution. So for any given system of linear equations, it will either have just one solution, or it may have infinitely many solutions, or it will have many, it will have no solution. Yeah. And a system of linear equations is said to be consistent if it has at least one solution. A system of linear equations which has at least one solution is said to be consistent. And a system of linear equations which has no solution is called an inconsistent system. So when there is no solution, we say we refer to the system as inconsistent. When there's at least one solution, we refer to the system as consistent. So the main goal is now to discuss, before even we discuss note number, if this was the other one, say equation, the system of linear equations given in, so we called it star. Given in star can be written as okay, before we write that one, you remember when you were in Form 3, if I give you 2x say plus 3y equals to 5, and then say 7x plus 8y equals to 10, these are two simultaneous equations in the variables x and y. Then we used to solve by a method called the matrix method. You remember something like matrix method of solving simultaneous equations? Hello? Yeah. So yes, there are elimination, then there's a substitution, but for me, I'm interested in the matrix method. Yeah, so you were to rewrite this in matrix form as 2, 3, 7, 8. Then you put this to form a matrix, and then you write x, y, and then you write 5, 10. You remember that structure? Yeah, so it's the same thing that we will be dealing with. So we'll be calling this matrix A, we'll be calling this variable matrix X, and we'll be calling this constant matrix B. So it's exactly the same thing that you are going to have. So we can write system star in matrix form as A11, A12, A13, all the way up to A1N, up then A21, A22, A23, all the way up to A2N, A31, A32, A33, all the way up to A3N, up to AM1, AM2, AM3, all the way up to AMN. And then we have X1, X2, X3, all the way up to Xn equals to B1, B2, B3, up to Bm. And then this will be calling it coefficients matrix A, this will be calling it variable matrix X, and this will be calling it constant matrix B. So which is simply mean that this equation alpha, equation star is or can always be written in the form AX equals to B. And that will be the most general form that we'll be using. So this is called coefficients matrix. This is what we call variable matrix. And this is what we call constant matrix. We can either call this one variable matrix or vector. We can call this constant matrix or vector. So methods of solving linear equations. One is what we call Gaussian elimination. Number two is what we call Gauss-Jordan elimination. C, Cramer's rule. And then other methods will be discussed later on, but these are the main ones that we are going to discuss. We also have what we call Jordan's, what we call the Jordan's method. Then we can also use what we call LU factorization. We can also have what we call Jacobi method, but the methods of interest in our discussion will be majorly these three. So I'm putting here ETC to mean that these are not the only ones that we can use to solve, but the interest of this course, these three are the main ones that you have to do. So before we stop, let's define what we call elementary. So we'll discuss each of these methods in details. But now what I want us to discuss is what will help us to really interpret and understand how to solve each of them. Solve the system of linear equations using each of the above methods. So there's what we call elementary row operations. So elementary row operations can be applied to system of linear equations or a matrix, and they simply help us to get a structure of a system of linear equations that can easily enable us to solve for the unknown variables in much simpler form than when the system is still in the precursor form. Like if I give you system like so before I set this one here, if someone gives you, say, x minus 2y plus 3z equals to 9, minus x plus 3y equals to minus 4, and then 2x minus 5y plus 5z equals to 17. And another person gives you the system x minus 2y plus 3z equals to 9, y plus 3z equals to 5, and z equals to 2. Call this system A, this other one system B. Which of those two systems will be easier to solve? The second one is easier because, in fact, the second one was the value of z without even writing down anything, 2. So with that value of z, you can replace in the second equation, and then you can get the value of y, okay? And then by the time you get the value of y, you already have z. So you replace the y and z and you get the value of x in much easier way, okay? Yeah, but this other one, the way they form the system is, may not be easy to work out the values of x, y, and z. So the elementary row operations helps us to convert systems which takes this awkward arrangement like in A to this nicer form in B that we can easily back substitute and solve the values of the unknown. So there are majorly 3 elementary row operations that we'll be discussing, or that are always available to be applied on any given system of linear equations or any matrix formed from a system of linear equations. And that can help us to generate what we call an equivalent system, which is easier to simplify or solve. So 1, interchange 2 rows. That when you have a system of linear equations, to arrange it, say, from the structure like A, the structure of B, we can always interchange 2 rows. Number 2, multiply a row by a non-zero constant. We are allowed to multiply a row of either matrix or a system of linear equations by a non-zero constant. And number 3, we are allowed to add a multiple of a row to another row. We are allowed to add a multiple of a row to another row. So these operations will help us to generate a matrix we call row echelon form, So row echelon form or matrix. So a matrix is said to be in row echelon form a matrix is said to be in row echelon form if it satisfies the following conditions or properties. One, all rows consisting entirely zeros if any, so because sometimes it may not be there, occur at the bottom of the matrix so if there are any rows that has all the elements to be zero, then it must be, or they must be placed at the bottom of the matrix. And remember, we are saying that if any, so sometimes that may not be the case. There may be no row with zeros. But if there is a row with zero, then you must place it at the bottom. Number two, for each row that does not consist zeros, the first non-zero element or entry. Remember the term element or entry have the same meaning here. Is one called a leading one. Number three, for any two successive non-zero rows, the leading one is the higher, in the higher row is further to the left than the leading one in the lower row. So any matrix that satisfy these properties is called a row echelon form matrix. This is what I mean by this property 3. You should not get confused. I mean, for example, if I have 1, 0, 0, 0 as my first row, then this does not necessarily has to be 0 numbers. It can be any number. So you see, for example, this is an example of a Rochelon matrix. This is first row. This is the leading one. This is the leading one. In the second row, this is the leading one in the third row. So this is saying that for any two successive non-zero rows, so for example, this is the first and second rows, the leading one in the higher row. So higher row, if you are comparing row 1 and row 2, higher row would be row 1. Or the row above the other row is row 1, is further to the left than the leading one in the lower row. So you say if you compare the first row and the second row, then if you're in the second, then the one in the first row is to the left. And if you compare second and third, one in the second is to the left of one in the third row. Similarly, if you compare first row and even the third row, one in the first row is to the left of the one in the third row. I don't know if that one makes sense to you. Yeah. In fact, yeah, I think that you're getting it here. So in fact, this is actually the arrangement we usually have, like a staircase. It's like a staircase here. Yeah. So that now, if you are in that staircase, then what is above is always to the left. So this one is here, then this other one is this one is here. I remember the same statement can be paraphrased differently. This thing can be paraphrased differently and say the leading one in the lower row is to the right of leading one in the upper row. It will have the same meaning. The leading one in the upper row in the lower row is to the right of leading one in the yeah. So then now, before I give an example for you to classify, and then we'll stop. Just say if if a matrix is in row echelon form and all other entries in the column corresponding to the leading ones are 0, then the matrix is said to be in reduced row echelon form. So we are giving another definition here, that if a matrix has satisfied all the characteristics of a row echelon form matrix, and further, all the entries in any column having leading one are zeros, apart from that leading one, then that matrix is said to be in reduced row echelon form. So to get to reduced echelon form, first you have to be in row echelon form. And then you add another condition that anywhere there's a leading one, then in that column, all other positions will be taken by zeros. So like here, this example, if I name this one A, B, C, D, E, and F. For me to have this matrix to be in reduced echelon form, then A must be 0. What other positions should be 0? D should be 0. YF. So you identify the positions of leading ones and then check through the column. So remember, column is moving top down, top down. Row is from left, right, left, right. Columns of a matrix are when you move from top down. Rows are from left to right. So this is what I mean. So once we have identified the positions, remember these are the positions of leading ones. So I mean now you check we check what is. So those are what we call rows. Not rows, those are what we call columns, not rows. Yes. And then these are what we call rows. So rows is from left to right. So these are rows, and then these are what we call columns. So what should we fix to be 0 for this matrix to be in row reduced echelon form? That really doesn't test anything. We only test where there is 1. We F. So we are saying that a matrix is in a matrix, if a matrix is in the row echelon form and all other entries in the column corresponding to leading ones are zeros, then the matrix is said to be in reduced row echelon form. So what matters is the column with leading 1. You don't go to just to any other random column. Columns that matters are those with leading ones. So then that doesn't really matter, or doesn't help in any way of classifying that as reduced row echelon form matrix. What matters is that 1, the matrix is in row echelon form. Once that is satisfied, then check where the leading ones and then identify those columns. So apart from that leading 1, everywhere should be 0 in that column that has a leading 1. So that is what makes the matrix to be classified as being in reduced row echelon form. So which other letter should be fixed to 0? Other letters or letter should be fixed to 0? I'm asking you, haven't given me the complete answer. We said we fix A to 0, we fix D to 0. Are those the only ones? Okay. So when there is no leading one, then so F really F you can F can take anything. Doesn't matter. It doesn't whether you make it 0 or don't make it non-zero, doesn't matter in the classification of this. Only those two. So D can take anything and it will be in reduced rational form. And then, so there's only A0 and D0. So B can take anything and still be fine. B can take any number. You are confusing what we mean by column and what we mean by row. So remember, our argument is with respect to columns. Argument is with respect to columns. Once you fix A to 0, okay? And then, So then is this a complete set? B should also be 0, okay? So then I'll say classify the following as row echelon form or reduced row echelon form or none. So consider this matrix 1, 0, 0, 2, 1, 0, minus 1, 0, 1, 4, 3, minus 2. Then the other one is, so let's call this matrix A, B, 0, 0, 0, 1, 0, 0, 0, 1, 0, 5, 3, 0. C is 2 minus 1, 4, 0, 0, 0, 1, 2, 4. D is 1 minus 5, 2, minus 1, 3, 0, 0, 1, 3 minus 2, 0, 0, 0, 1, 4, 1, 0, 0, 0, 0. E is 1, 0, 0, 2, 2, 0, minus 3, 1, 1, 4, -1, -3. And F is 1, 0, 0. Two, 0, 1, 0, 1. Okay, -1, 0, 0. So -1, 0, 2, 2, 0, -4. Those are enough to make us understand. Can you be trusted with A to classify it? Is A row echelon form matrix? Yeah, so the first thing that identify the leading ones. So we have this, we have this, we have this. So it satisfies all the properties that this now happens. Every row is a non-zero row, so there are no exclusive zeros. And we have leading one such that the upper row leading one is to the left of the leading one of the lower rows of all the three consecutive rows, okay? Yeah, so this is in row echelon form. Can we say it is in reduced echelon form? It is not because of this 2 and this -1, okay? Yeah, good. B, is it in row echelon form? So the first thing is to identify the leading ones. And then this is in row echelon form because one, there exists a row which has all zeros and it is placed at the bottom of the matrix, okay? And then the non-zero rows, the leading one of the top row is to the left of leading one to the lower row. So this is okay. This is in row echelon form. And can we say it is in reduced echelon form? Yeah, it is also in reduced echelon form because because it's all satisfies all the properties of or all the conditions of echelon form, the leading ones which exist for this matrix happens to be the only non-zero elements in their respective columns. Okay. Yeah. So this also in reduced row echelon form. C, is that matrix in row echelon form? Okay. Why? Yeah, that's the first mess. That the matrix happens to have a row that has all the elements to be zeros, but is not placed at the bottom. Okay. So in fact, that's enough to say that this is not in row echelon form. And then another thing, assuming even if we had placed this at the bottom, if we put zero here, we put zero here, we put zero here, then one, then two, then four. Will it be in row echelon form? Why? So remember, this is the first non-zero element here is two, but the remember the first non-zero element must be one, not this number two. So that's still a mistake. And even if it was one, it will not still be a rational form, because if you put one here and one here, then you can't say that the top one is to the left of the lower one. Okay? Yeah, so this is not in rational form. D. Why are you worried of -5? You shouldn't remember once now. This is what matters. This first non-zero numbers in each row. -5 has nowhere to worry you, because -1 is in the row, the first row, and the first row leading one has already been determined. So that's it. Mm. Okay, maybe paraphrase your question, or yes, like. Mm. So the thing is that what you have to first determine is that check that there is, if all rows are non-zero, and non-zero mean that at least there's a number that at least there's one non-zero number in a row, then that first number must be one. One, remember we were counting it from this left-hand side. Okay? So you have a pick that this one, this one, this one, this one. So once, like for instance, in this first row, we have seen that the first non-zero number is one. So -5 has no problem. It doesn't disturb us, because the condition for having the leading non-zero number to be one has been determined. Then the other thing is that for the other non-zero rows, their leading ones must always be to the right of the one on this top row. If you now measure, if you make your top row to be a measure, each leading one must always be to the left of other leading ones on the lower rows, or other leading ones of the lower rows are to the right of that leading one in the top row. I don't know if I'm confusing with the word left and right. Yeah, because so once you have identified that, then you don't just measure one and two. Like if you have this one here, if this one in the third row was placed at this position, then this matrix will fail to be in rational form. Assuming the one here at this position was at this point here, but the second one has been placed where it is, then this matrix will not be in rational form, because the condition of the positions of leading ones of consecutive rows will be wrong with respect to second and third row. I don't know if that you were able to see that. Yeah, so if one was here, then this matrix will not be in rational form. Okay. Yeah. So the structure in which it is in rational form. Is it in reduced rational form? Why? Mm. So remember we say that once we have confirmed that the matrix is in row echelon form, to check that the same matrix is in reduced row echelon form, you just identify where they are leading ones. Once we have identified where they are leading ones, check that everywhere there's a leading one, that column, that is the only non-zero element. Other things are zero. Where this leading one is what determines the reduced row echelon form of the matrix. You identify where the leading ones are, and then check through the columns where they belong. Are every other element zero? If that is the case, then it's in reduced echelon form. Mm. 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 We have said that column means moving from top to down. So the first thing that circle where they are leading ones, this one I've done it. So we are checking now. We are checking this. We are checking this. We are checking this. We are checking this. That's what you call columns. So then you ensure that of those columns, the leading one is the only non-zero element or entry. All other things should be zeros. That's the meaning of all other things, yes. Yeah, this is not in Russian form. So remember, like already 2 is not 0 at this point here. There's the problem here with 2, there's a problem here with -1, 3. Yeah, so these are the things with the zeros. E. Why? What makes it not to be in Russian form? Mm. Mm. Remember, please, come again. Note that when we're explaining about the things of zeros, we said if any, there is not a condition that they must be there. I don't know if this is making sense to you. That all rows consisting of entirely zeros, if any. So it means that if there exists a row that has all the elements to be zeros, but it's not a condition that for any row echelon form matrix, it must have zero column rows with zeros. It's just that if it happens to have row with all the elements to be zeros, then it should be at the bottom, but does not mean that it need to have it. I don't know if that makes sense to you. Okay. So then now, so you cannot argue that you are saying the E is not in Rochambeau form because it doesn't have zero, a row with zero elements. Mm. If the row is not a zero row, non-zero element should be 1, but in this second row, there's a problem here, okay? Yeah, so the condition is that if there's a row that is non-zero, and non-zero means that at least there's a non-zero number in that row, then the starting non-zero number must be a 1, okay? Which is not satisfied by E. So assuming this 2 was 1, will it be in Rochland form? Yes. Assuming we made it to be 1. So it will be in Rochland form, okay? But in its form, the way it is, this is not. Is it in reduced Rochland form? It can be, because for you to arrive at reduced Rochland form, you must have passed through the step of Rochland form. So if you say it is not in Rochland form, then you cannot say it is in reduced Rochland form. Yeah. If row echelon form or not. Why? That's not the explanation. Yes. Mm. But that's really what we have. That one we don't. That one is not disobeyed. It's there. What you are saying is there. So Mesema, know that a row that doesn't have a row, actually non-zero rows, the first element should be 1. As in you see this. Then the third and fourth. E matrix is how many rows? How many rows are in this matrix? 3 rows. Yeah, that's a easy kwa. Whereas unapata pi number 4. Yes. Number that condition for the here. For the 2 successive non-zero rows. I hope you understand what you mean by successive. Next to each other. In fact, you can just say the leading one in the higher row is to the left of leading one in the lower row. Still makes sense. In fact, if I delete this, it's to the left of the leading one in the lower row. Just like what we have shown in this staircase. But this is what is row above. So this element 1 is to the left when you compare with this other next row 1. And here we'll have 0, here we'll have 0, this will be 0. Why is this not in rational form? Yes, your answer is right, but you are not giving the correct explanation. Yes? Mm. You know the answer, but you know the answer, but you want to complicate your life for no reason. By the way, how are you seeing this number from your end? Maybe it's the one, maybe you read this as, yeah, this is a 0. So if you are seeing this as 0, then you should not be confused on what you need to explain. I thought maybe my handwriting is what is making you to struggle. But if you are able to say that is a 0, then you should not struggle to explain. And that's what I want you to explain. That's what I want you to explain. So this matrix is not in row echelon form on arrival. Reason, it has a 0 row that is not placed at the bottom. Second row consists of all zeros. Third row is having non-zero elements. And we said in the first condition that if there exists a row with all the elements to be zeros, then it must be at the bottom. And so here, the 0 row is not at the bottom of the matrix. If we swap row 3 and row 2, then that matrix will be in rational form. Yeah, if we interchange row 2 and row 3, the matrix will be in rational form. And so that is what the work of elementary row operations does. You are allowed to switch 2 rows, or to interchange 2 rows. And so when you interchange row 2 and row 3 for F, it will now convert the matrix into rational form. In E, if you multiply the second row by a half, it will also be now in rational form. Okay. Yeah. And so next session, we'll be discussing on how to convert matrices which are not in rational form into rational form and further into reduced rational form. And as we shall say in the discussion of Gaussian elimination simply means you convert the system of linear equations into matrix form, then change the coefficients matrix A into rational form. Once you convert the matrix into rational form, use back substitution to solve the system. Then for Gauss-Jordan elimination, we will now reduce the matrix into rational form, go further, reduce it into reduced rational form, and then get the values of the unknown variables. And what is in the Cramer's rule will do it later after discussing about determinants of matrices. So it helps to solve, it solves systems of linear equations once you understand the concept of determinant of a matrix. So that's what we'll discuss in the next session. Can stop at that point. So have a good evening. Yeah, good. So tomorrow we are meeting for the integral calculus. Remind Valentine to be present. But if he doesn't come.